This is Miss List, and today we are taking a look at 2.6, which is on resonance and something called formal charge. In 2.5, we talked about how to draw Lewis dot structures, and I made a mention that sometimes there is more than one structure can be drawn. And I think I used the example of carbon dioxide. One structure looks like this with a double bond on each side, and one looks like this with a triple bond and a single bond. And I said that there is a way to know which one is correct because technically they're both valid. Both of them have the correct number of electrons. Both of them have completed octets. So which one is the preferred structure, if you will? And it turns out that this one with the double bonds on each side is preferred, and this one is not. And the way we figure that out is by doing something called formal charge. You calculate formal charge for every single atom that's in the molecule. So I would calculate a formal charge for this oxygen, I would calculate a formal charge for carbon, and I would calculate a formal charge for oxygen on this side as well. So the way we determine formal charge is you take the number of valence electrons and you're going to subtract lone pair electrons, and then you're going to subtract the bonds. So if I was going to do, and I'm going to erase here, my formal charges for this first structure, and remember we do one for every single atom that's here. I'm going to do a formal charge for this oxygen. This oxygen has 6 valence electrons. I subtract 4 lone pair electrons. And then I'm going to subtract 2 because those are how many bonds there are there. So the formal charge on that oxygen is 0. Similarly, if I was to do the formal charge on the oxygen on the right, we have the same situation. 6 valence electrons minus 4 lone pair electrons minus 2 bonds, and I get a formal charge of 0. And then similarly for carbon here in the middle, we have 4 valence electrons minus no lone pairs minus 4 bonds, and I get 0. This is preferred. Formal charges with zeros on all the atoms means that this is a really stable structure. And that is the goal. We want as many zeros as possible. Now, if I compare that to the other way that we drew the carbon dioxide, I'm just going to erase here and bring it back on the bottom. And just for reference, I'm going to just put the formal charges. These were all zeros. If we go back and redraw the triple bond oxygen with a single bond oxygen and calculate the formal charges here. Again, I'm going to take my valence electrons, which is 6, minus 6 lone pair electrons, minus 1 bond. That means this atom is going to have a -1. Carbon has 4 valence electrons, minus no lone pairs, minus 4 bonds, so carbon still has 0. But then this oxygen, 6 valence, minus 2 lone pair electrons, that's these guys over here, minus 3 bonds. This gives me a +1. So when I compare the formal charges for this structure, I have a -1 on that 0, or the oxygen atom. I have a 0 on carbon, and I have a +1 here. That's what makes this one not preferred. Again, we want the structure where as many of the atoms have this formal charge of 0. And that's how I can tell if this is an appropriate structure. Because mentioned before, sometimes you can draw more than one option. And that's where this concept of formal charge comes in. So let's look at some examples. Here we have an example of this actually is written wrong. This should be N2O. All the pictures are correct though. So we have 4 different options for N2O. And again, all of them have the correct number of electrons. All of them have octets. octets where needed. Well, actually, some of them don't have octets, and we see that here on the nitrogen and on the oxygen. So I would bet that it's not going to be this one, and it's not going to be this last one. Again, if you look at nitrogen, nitrogen only has 2, 4, 6 electrons around it. So nitrogen does not have an octet. We don't like that. Over here, similarly, oxygen doesn't have an octet. Oxygen only has 2, 4, 6. So oxygen does not have an octet. Again, we don't like that. So I can eliminate, if this was a multiple choice question, I can eliminate C and D because those do not have octets. And then that leaves me with A or B. It does appear that everyone has an octet. So this is where we would move and do our formal charge calculation. So nitrogen has 5 valence electrons. I'm going to subtract 4 lone pair electrons, and I'm going to subtract 2 bonds. So this is actually essentially 5 minus 6, which gives this a -1. I have this nitrogen valence electrons 5 minus no lone pairs minus 4 bonds. So that's going to give me a +1. And then for this oxygen, I have 6 valence electrons minus 4 minus 2. So oxygen is the only one that has a 0. So I'm just going to write these above: -1, +1, 0. On the one in the middle, we're going to do our formal charge calculation again. I have nitrogen here in the middle, or sorry, the left side nitrogen has 5 valence electrons minus 2 lone pair electrons minus 3 bonds. That's going to give a 0 for the first nitrogen. I have 5 valence electrons minus 4, which gives me a +1. And then the final oxygen, I have 6 valence electrons minus 6 lone pairs minus 1 bond. So that's going to be -1. So I'm just going to write these across the top: 0, +1, -1. So I don't have a situation like I did with the carbon dioxide where all of them are 0. So I need to make a judgment call here. And the key to deciding is I want to make sure that if we have to have a negative charge, that it goes on the most electronegative atom. So if I were to pull up my periodic table, the oxygen is going to be more electronegative than nitrogen is. Again, the closer we get to fluorine, the more electronegative you are. So in this case, I would choose structure 2. If this was multiple choice, maybe this is B and this was A. And the reason I chose that one is because it's going to put this -1 on the most electronegative atom. So that's why I chose that. All right, here we have a second example where we've got 2 different versions of sulfate ion, and they want us to determine which one is most valid. So on the sulfate on the left, each oxygen is going to be the same because they all have 6 valence electrons and 1 bond. So for oxygen, it's going to be 6 valence electrons minus 6 lone pair electrons minus 1 bond. So all the oxygens are going to be -1s. So -1, -1, -1, -1. For sulfur, it has 6 valence electrons. There are no lone pair electrons and it has 4 bonds. So that actually gives me a +2 on sulfur. On the right, we have a different version of sulfur. And the interesting thing here is that sulfur has more than an octet. If you look around the central atom on sulfur, it has 2, 4, 6, 8, 10, 12 electrons around sulfur. We mentioned in 2.5, that's okay. There are some that can have expanded octets. We see this with phosphorus, sulfur, iodine a lot. And formal charge helps us explain why this happens. So for this oxygen on the left, it's going to be similar to what we saw in the first example because it has 6 valence electrons, it has 6 lone pair electrons and 1 bond, so it's going to have a -1, as will the one on the right, because it's exactly the same. The oxygens on the top and the oxygens on the bottom, though, we have 6 minus, because 6 valence electrons, minus 4 lone pair electrons, minus 2 bonds. That oxygen now has an electronegative, or formal, of 0. And then if we look at sulfur, sulfur has 6 valence electrons, minus no lone pairs, minus 1, 2, 3, 4, 5, 6 bonds. Oh my gosh, look at that. The 2 oxygens, the top and the bottom, have gone to 0. Sulfur is now a 0, so I've reduced the net charge here. And oxygen is the most electronegative, and it has a -1 charge. So if I was choosing the most appropriate Lewis dot structure for sulfate, it's going to be the one that has the least amount of charge associated with it, and it's going to be the one that has the most electronegative, having a negative charge. Now, understandably, this does get to that with an expanded octet, and that's one of the reasons that expanded octets are okay, is because they often reduce the formal charge. The second part of 2.6 has to do with something called a resonance structure. And a resonance structure is where we can draw the location of a double bond or triple bond in different positions. So here in this example for the nitrite ion, NO2 - 1, on the left, we can see that the double bond is here on the left side of the atom. But on the one on the right, we can see that our double bond appears to the right-hand side. And just that switching of the double bond from one side to the other side creates what we call resonance structures. And so again, these are very similar to each other. The only thing that is different here is that we've changed the location of the double bond. On one, it's on the left, and on the other, it's on the right. Now, in real life, neither one of these molecules actually exists. And that's where this idea of resonance happens. What they found is that when we have different resonance structures possible, there's not a specific single bond and there's not a specific double bond on one side or the other. And in fact, it's an average between a single and a double bond. And so in real life, those bonds we would actually call a 1.5. They're not a single, but they're not a double. It's somewhere in between. Sometimes you might see this structure drawn where we've got the oxygens on both sides, and they use dots to show that those electrons, it's not really a single bond, it's not really a double bond, that this is a resonance structure, and that those bonds there are 1.5 instead. Different structures can have different number of resonance that can be different molecules can have different number of resonance structures depending on how many bonds they have. So in this next one, we have draw all the resonance structures for carbonate. So just as a review from 2.5, carbon has 4 valence electrons. Each of the oxygens give me 6. And then I get to add in an extra 2 from the -2 charge. So this is going to give me a total of 24 electrons to make this work. I'm going to put carbon in the middle. I'm going to connect my oxygens on each side. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I notice that carbon does not have an octet. So I'm going to remove 2 of these electrons and bring them here and make a double bond. And usually when we have an ion, we put brackets around it to show that this is an ion and that we've added 2 electrons. So now that we've drawn one structure, they want us to draw the resonance structures for that. So the resonance structures are going to look identical to what we just drew, we're just going to move the location of that double bond. So maybe in the next structure, I put the double bond going to the right. And then everything else is the same. And then I can create one more if I have the double bond pointing down. So this time I'm going to have the double bond point down, electrons on the left and right, or oxygens on the left and right, only a single bond. The one that has double bond has 4 lone pair electrons, and then again putting that bracket around it, telling everyone that this is an ion. So what makes these resonance structures, again, is the location of that double bond is moving. Here, our double bond is on the left. Here, our double bond is on the right. And on the last one, the double bond is going down. Now, the question becomes, what is the average bond length for this? And we talked about earlier how when you have a double bond and a single bond, it's going to be kind of in between. And that's why we had a bond length of 1.5. Well, in this example, we have a double bond and a single bond. And I'm going to divide that by my total number of bonds. So if I take 4 divided by 3, I get an average bond length of 1.33. So again, not quite a double bond, not quite a triple, or not quite a single bond, not quite a double bond. Final example, they want us to draw the most valid Lewis dot structure for PO4 with a -3 charge, then draw all the relevant resonance structures. First thing I'm going to do is I'm going to add up my valence electrons. I have 5 for phosphorus. I have 6 for each of the oxygens, and I have 4 of them. And then I've got an extra 3 because the -3 charge means I get to add in 3 extra. 32 total. I'm going to phosphorus in the middle, and I'm going to connect everyone using single bonds. And then the extra electrons are. So this is one option of our structure. And if I was to do our formal charge, so I'm just going to come down to the bottom and do formal charge. I have 6 valence minus 6 lone pair electrons minus 1 bond. Each of the oxygens are going to have -1s. So I'm just going to include those -1s, 1, -1, -1. This is going to be 5 valence bonds because there are no lone pairs. So what I see that we've got a positive on my central atom, and then I've got some negatives here. Now, like I mentioned before, technically, this isn't wrong, but is it the best we can do? And the answer to that is no. It's because you might have remembered from yesterday, we watched the 2.5 video, that I mentioned that phosphorus can have what's called an expanded octet. And so what I want to know is, what if I took one of the lone pair electrons off one of the oxygens, that reduce, and the answer is going to be, now the oxygens that didn't change one. The oxygen at the top, though, is going to be a 0 because we've got 6 valence electrons minus 4 lone pairs minus 2 bonds, 0. And then my phosphorus is also going to go, because I have 5 no lone pairs but 5 bonds, is now a 0. So just by making that one, I've reduced the charge on each atom, or on 2 of the atoms, which makes this an overall more favorable structure. So that is, as I mentioned, one of the reasons that we have expanded octets in the first place is because it helps reduce the formal charge involved. So I would say that this is a valid structure for phosphate. I'm putting it in brackets and with the -3 so that anyone else knows I've added 3 additional electrons. Now, to do my resonance structure part of this, I'm going to draw some of the same structure. The only difference is I'm going to change. So in one, I'm going to on the next one, we are going to put the, and in the final one, we are going to put that double. So the number of resonance structures that can be drawn really depends on the structure of the particular molecule we're drawing. Sometimes there might just be 2 resonance structures, sometimes there might be 3, 5, or 6. But the point is that all I've done to create these resonance structures, once I decided that this was the valid one that had the lowest formal charge, is I moved the location of the double bond. It's going to the top, it's going to the right, it's going down, and it's going to the left. And that's what makes these resonance structures of each other. All right, thanks for listening. Next time.